Hello there, Mr. Sutton here with the AB Calculus 513 Extra Practice Number 1 solutions on average value. For this problem, we're trying to find the average value of this polynomial on this interval, and this was a no calculator question. So let's go ahead then and set up our average value setup. That's going to be 1 over b minus a, so 1 over 1 minus 0, which is just 1, times the integral from 0 to 1 of all that stuff, dx. Next, let's take our antiderivative. Now we're just going to have a 1 out in front of everything, so we don't have to worry about some weird fraction out in front. But we do need some antiderivatives. So we've got, if we bump this up to a 6 and divide, negative 1 over 6 x to the 6th. And then this bumps up to a 4, so that's 3/4 x to the 4. This becomes a 2. Dividing by that, we have negative x squared. And then this will become negative 3x. Again, evaluated from 0 to 1. So now I'm going to do 1 plugged into all that stuff, minus all this stuff with 0 plugged in. Now the good news is all the stuff with 0 plugged in just goes away because we're multiplying by 0. So we just have to look at this first batch of numbers. And these all have 1s in them, so this is also pretty easy to put together. This is just negative 1/6 plus 3/4 minus 1 minus 3. And it's free response, so you actually didn't need to simplify any further than this line. But if we do here, this is going to be, let's see here, this is negative, if we get a common denominator, negative 2/12 plus 9/12, that's 7/12 minus 4. So this is like having 7/12 minus 48/12, which is going to be negative 41 over 12. For this problem, I'm trying to find the average value of this piecewise function on the interval from 2 to 5, and I can use a calculator, but first I'm going to have to set up the integrals so I can plug them into my calculator. So my average value, I'm going to have 1 over b minus a, so 1 over 5 minus 2 times, and now I'm going to have a combined kind of integral here. So I have one integral for this first rule from 2 to 3, so that's going to be x minus 6 for the integrand with the dx. Plus, I need an integral from 3 to 5 for this second rule, so 3 to 5 of negative x dx. And now it's time for the calculator. So let me show you what I've got so far. I have the 1 over 5 minus 2, integral from 2 to 3 of that first function. And now I'm going to do plus, and then for the other integral, we're still doing math 9 for integrals. Now I'm going from 3 to 5, and I have the function negative x, and then dx. And you can close the parentheses if you want. And that all comes out to negative 3.833 if you round it off. For this no calculator problem, we're trying to find the average value of this polynomial over the interval from negative 1 to 2. So this one actually takes a while, but let's start the setup here. So we have 1 over b minus a for average value, so that's 1 over 2 minus negative 1, times the integral from negative 1 to 2 of this function here, 3t cubed minus t squared dt. And that's going to be now 1 over 3 times, now let me take my antiderivative. So this bumps up to a 4. We've got 3/4 t to the 4th. Minus, this will be 1/3 t cubed. And that's being evaluated from negative 1 to 2. So before I go ahead and expand this, often I leave this number outside. But this time around, I'm actually going to go ahead and distribute this inside, and I'm allowed to do that because at the end of the day, everything is just being added or subtracted. So this is going to become, let's see here, 1/3 times 3/4, the 3 cancels, so I've got 1/4 t to the 4th, minus, this is going to be 1/9 t cubed. And the reason I'm distributing that 3 in there is so that I have less fractions to deal with at the end of the day. I don't know, half a dozen of one, 6 of the other. So expanding this now, I have all of this stuff with 2 plugged in, minus all of this stuff with negative 1 plugged in. And unfortunately, I can't just leave it like that because the answer choices are simplified. So let's just see what we have here. This is 16 over 4, so that's a 4. And this is, let's see, the 8 times the 1, that's an 8/9 minus 8/9. Over here, this negative 1 to the 4th is just a 1. So I have a 1/4, but everything in here is being subtracted, so this is negative 1/4. And then finally over here, this negative 1 to the third becomes a negative 1. That makes this a positive 1/9, but it's being subtracted, so it goes back to being a negative 1/9. So careful with your signs on this one. Now, to make my life a little bit easier, I'm going to combine the ninths first. So negative 8/9 minus 1/9 is negative 9/9, which is just negative 1. 4 minus 1 is 3. 3 minus 1/4, that's 12/4 minus 1/4. So that's going to be 11/4, which finally gives us answer choice A. On this no calculator problem, we're trying to find the average value of radical x over the interval from 0 to 2. So we are going to do 1 over b minus a, that's 2 minus 0, times the integral from 0 to 2 of the square root of x. But I'm going to write this as x to the 1/2 dx, just so I can use my reverse power rule a little bit more easily. So I've got 1/2 times, this bumps up to the exponent 3/2. Dividing by that, we have 2/3 out in front. And just to make my life a little bit easier, I'm actually going to multiply this 1/2 in here. So that's going to be, let's see here, 1/2 times 2/3, the 2's cancel. So this is just going to be a 1/3 that this becomes. And now I'm going to just do, let's see, this stuff with 2 plugged in minus this stuff with 0 plugged in. So I'm going to have the square root of 2 cubed minus the square root of 0 cubed. And all of that gets multiplied by this 1/3, because again, I did 1/2 times 2/3 at the very beginning so that I didn't have to mess with so many fractions. All right, so this is, let's see, the square root of 0 is just 0, so we don't have to worry about that. But what is this radical 2 to the third coming out to? Well, this is radical 2 times radical 2 times radical 2. So if we simplify that, that becomes 2 radical 2. But that's going to be on top of a 3 here because you're multiplying it by 1/3. So this is going to then be 2 radical 2 over 3, which ends up being, let's see here, the closest answer choice is choice C. For this calculator question, we're trying to find the average value of radical cosine on the interval from 0 to pi over 2. Let's set up the integral, and then we'll plug it in our calculator. So for this, we need the average value formula. That's 1 over b minus a times the integral from a to b of the thing you're averaging. So in this case, we have 1 over pi over 2 minus 0, which of course is just pi over 2, times the integral from 0 to pi over 2 of radical cosine. So let's plug this in the calculator. So at the end of the day here, I plugged in 1 over pi over 2. I could have written minus 0, but why bother? We're going from 0 to pi over 2. We have all that radical cosine business and a dx, and this comes out to, now it's thinking about it, yep, 0.763, and that's answer choice C. On this problem, if f is continuous and strictly increasing on the interval from a to b, which has to be true, so these all involve integrals from a to b, so it's important to keep in mind that the integral from a to b, you're basically talking about the area under this f curve between a and b. So this area here, the true area. And now this first one, they're saying that that area is less than f of b times b minus a. Well, what does that mean? B minus a is the base, and if you're multiplying it just by a single number like f of b, you're essentially finding the area of a rectangle that has a base of b minus a and a height of b. So this rectangle here. Now they're saying that the true area is going to be less than that, and that's going to be true. You're basically doing you're doing RAM, this is a right Riemann sum approximation if you're using this right endpoint, and we know that increasing functions, our RAM is going to overestimate those. So that means that the true value would be less than the RAM estimation. For this next one, we're doing f of a times b minus a, so that's this smaller rectangle here, essentially an LRAM approximation. And here they're saying that the true value is going to be bigger than the LRAM approximation, which is true, because LRAM is going to underestimate increasing function area. So these are both true, and you could see it just by drawing little rectangles on here. This next one is kind of weird. They're saying the area equals f of c times b minus a for some number c such that c is between a and b. So this is one where if you've never seen the mean value theorem for integrals, this one is a little out there in left field. Basically, though, the mean value theorem for integrals says that if you have a continuous function, then there is some x value in here that if you get the y value and make a rectangle out of it, that area is going to equal the true area of your integral. So this is actually going to be true because our function's continuous. This is just the MVT for integrals. So also true. That means that it's choice E, options 1, 2, and 3. For this problem, they want the average value of 1 over x on the interval from 1 to 3. So average value, that's 1 over b minus a, so 1 over 3 minus 1, times the integral from 1 to 3 of 1 over x dx. So that's 1/2 times the antiderivative of 1 over x, which is ln of absolute value of x, evaluated from 1 to 3. Now here you actually don't need the absolute value since you know you're only going to be plugging in positive numbers, but it doesn't hurt to leave it in temporarily. So now multiplying this out, we've got 1/2 times ln of 3 minus ln of 1, which of course doesn't match any of the answer choices, so let's keep going. The ln of 1 is 0 because you're asking what do I have to raise e to get 1, and that's going to be 0. Log of 1 is always 0 no matter what log it is. So this is just 1/2 times the ln of 3, which is just going to be ln of 3 over 2. Choice D. For this problem, we have the temperature in Celsius of the water in a pond, and we have a differentiable function w that gives us that temperature. So let's see here. We want to approximate the average temperature in Celsius over the interval from 0 to 15 using a trapezoidal approximation. And we have subintervals with length 3 days, which is good because that's all they gave us in this table. So let's get our general setup. Average value is going to be 1 over b minus a times the integral from a to b of our function. So that's going to be 1 over 15 minus 0 times the integral from 0 to 15 of the w function, because that's what we want the average value of. And now we're going to launch into our trapezoidal approximation. Since this is free response, I'm going to be very careful about writing equals. I'm actually going to write a squiggly equals here, approximately equals, and I'll start with the 1 over 15. Because if I write equals, then I'm saying that the average temperature is whatever I write here, but we don't know that for sure. We're just approximating the average temperature on this incomplete table information. So let me get some trapezoids here. I've got my first trapezoid is going from 0 to 3, so that's going to be 20 plus 31 over 2 times a height of 3. Then I have 31 plus 28 over 2 times a height of 3. It's always going to be a height of 3 because we've got subintervals of length 3. Next, we have 28 plus 24 over 2 times 3, 24 plus 22 over 2 times 3, and 22 plus 1 over 2 times 3. And if you just put degrees Celsius on the end of this, because the units are going to be the same as the original function that you're averaging, you would actually be done. But if you want to do this on the calculator, you could. To do this efficiently on the calculator, I noticed that I'm multiplying all of these fractions by 3 and also dividing all of them by 2. So I've essentially got a 3 halves that I can pull out of here. If I do 1/15 times 3 halves, well, that's, let's see, 3 over 15 would be 1/5 times 1/2 would be 1/10. So I've essentially got 0.1 that I'm going to be multiplying everything by. And now that I've pulled out the 3 and the 2, I can just really add all these things together. So I'll just do this off camera. So I basically did 0.1 times all of these numerators added together. And pressing enter, I get 25.1. And again, that is degrees Celsius. For this next part, this depended on information from a previous part, so I included the relevant part from part C here. So a student proposes a function p as 20 plus all this stuff as a model for the temperature of the water at time t. And we want to use that function p to find the average value of p of t over time, over the interval from 0 to 15. So this is another average value problem, but this time we're going to use the calculator for the bulk of it. So we're going to have 1 over 15 minus 0 times the integral from 0 to 15 of the p of t function now. And I'm not going to bother rewriting it because they wrote it for me already. I'm just going to plug it in my calculator. So here we go. I've got 1 over 15 times integral from 0 to 15 of, well, the hardest part of this was basically entering that function in there. But once I've got it, I just press enter. And I get 25.757. And again, that's going to be degrees Celsius. For this problem, we have a metal wire of length 8 centimeters heated at one end. The table above gives selected values of the temperature of the wire x centimeters from the heated end. So clearly, as you go further and further from the end that's being heated, a bigger distance, it's not going to be as hot. Heat doesn't conduct as much over the distance there. So we want to find an integral expression now for the average temperature of the wire. So for average temperature, we need to do 1 over b minus a. So that's going to be 1 over 8 minus 0 times the integral from 0 to 8 of, and we want the average temperature of the wire. Well, temperature is represented by T of x. So we're just going to write T of x dx here. And the next thing they want us to do is estimate that average using a trapezoidal sum with 4 subintervals. So I am going to write approximately equals 1/8, and you've got to have the approximately there because you're estimating. This is not the true value. And now for a parentheses with a whole bunch of trapezoidal fractions in there. First fraction, I'm going to have 100 plus 93 over 2 times a height of 1. Plus, we've got 93 plus 70 over 2 times a height of 4 to get from 1 to 5. Plus 70 plus 62 over 2 times a height of 1. And finally, 62 plus 55 over 2 times a height of 2. There we go. All right. So you could actually leave it like this. And since this is average temperature, just put the units in there, which is degrees Celsius. Or since this is a calculator problem, you could actually crunch the numbers, which I'll do now. And if we plug all that in, it comes out to that weird fraction, which I'm going to math decimal that, to get 75.688 degrees Celsius. For this part of the problem, they want us to find the integral from 0 to 8 of t prime of x dx and indicate units of measure, and then explain it in terms of the temperature of the wire. So taking the integral here, basically we need to find the antiderivative of t prime, and that antiderivative is actually just going to be t. So we're taking t of x from 0 to 8, so t of 8 minus t of 0. And we actually have a table that tells us values of t at those times. T of 8 they told us was 55. T of 0 was 100. So we're doing 55 minus 100, which is going to be 45. Or actually negative 45. Negative 45 what? Well, T is in terms of degrees Celsius, so this is negative 45 degrees Celsius. Now what does that actually mean? Well, let's look at what we're integrating here. T prime is the change in temperature, or the rate at which the temperature is changing, I should say. The rate of change of the temperature. So if we integrate that, we're getting the total change in the temperature from 0 to 8 centimeters. Specifically, what's happening essentially if you have a negative 45 degrees Celsius is that your temperature of the wire is dropping 45 degrees Celsius as you go from 0 to 8 centimeters away from the heat source.